Good evening, and welcome as always to The Sleepy Scientist. I'm so glad you could join me. Tonight we drift towards one of the most profound ideas in all of physics, quantum fields, and the part they may have played in building reality itself. First though, a brief and honest word. You've probably noticed there are no ads on these videos, so nothing will break the quiet tonight. Keeping it that way does take a little help though, and the best way to lend it is the ebook. If you have a spare minute, and only if you do, pause here and take a look. There's a QR code on screen throughout, and a link down in the description across to the website, theleapyscientist.com. It's an unhurried, patient guide to quantum physics, the ideas behind these videos given a little more room to breathe, with the full narrated audiobook alongside. Honestly, a quiet look really is the most helpful thing you can do to keep these videos coming. That's all I'll ask tonight, and I ask it warmly. Thank you. Now, I would love to know where in the world this reaches you. Perhaps you are settled in bed with the lamp turned low. Perhaps you're walking somewhere peaceful in the dark or resting quietly while the world outside busies itself with its usual clatter. Wherever you happen to be, ease yourself in slowly and let the day begin to lose its sharpness. Tonight's idea is among the deepest in modern physics, which brings a small hazard. It may rouse the mind rather than lull it. Still, there is comfort in that. Should sleep keep its distance for a while, it will do so alongside a clearer sense of why the universe may not be built from tiny solid specks at all, but from fields, ripples, quiet interactions, and rules we never see. So let us begin gently. How did quantum fields build reality? At first glance, reality seems wonderfully solid. A stone rests in the palm with a reassuring weight. A wooden table resists the hand placed upon it. A planet turns beneath the feet with such steady confidence that it feels almost rude to question it. Even stars, though made of burning plasma rather than rock, seem to possess a kind of grand physical certainty. They shine, they pull, they occupy space, they behave like things, and for ordinary life, that picture works beautifully. The world appears to be made of objects. Objects seem to be made of matter. Matter seems to be made of atoms, and atoms, in the familiar schoolroom picture, seem to be made from tiny particles, with electrons somewhere outside and a nucleus tucked inside like a very serious little central office. But modern physics asks for a stranger kind of patience. The deeper it looks, the less the universe resembles a collection of tiny hard beads. The solidity of matter is real in everyday experience, but it is not the deepest layer. It is an outcome. It is something built from rules, interactions, quantum states, energy levels, and fields that cannot be seen directly in the way a stone or a hand can be seen. The first unsettling clue is that atoms are mostly empty space, at least in the simple geometric sense. If the nucleus of an atom were imagined as a small object near the centre of a large room, the electrons would not be little planets neatly circling close by. The atom's size is enormous compared with its nucleus. The nucleus contains almost all the atom's mass, while the surrounding electron structure gives the atom its volume, its chemistry, and much of its behaviour in the world. Yet this does not mean matter is secretly hollow in the casual sense, as though a table should be easy to pass through with a confident enough stride. The emptiness inside atoms is not the same as nothingness. It is structured by the electromagnetic field, by the electron field, by quantum rules, and by the allowed energy states that electrons can occupy. A hand does not pass through a table, because the charged particles in both are governed by electromagnetic interactions and quantum principles, including the Pauli exclusion principle, which prevents certain particles from all piling into exactly the same quantum state. Reality is not solid because atoms are packed like bricks. It is solid because fields and quantum rules organize matter into stable patterns. This is where quantum field theory enters quietly, carrying one of the most important changes in the history of physics. In ordinary speech, particles sound like tiny objects. An electron sounds like a little dot. A photon sounds like a little packet of light. A quark sounds like something tucked inside a proton or neutron, very small and very difficult to invite to dinner. But in quantum field theory, particles are not treated as the most basic things. They're excitations of underlying fields. An electron is understood as an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons are excitations of gluon fields. The Higgs boson is an excitation of the Higgs field. The field is the deeper object in the theory, and what is called a particle is a detectable ripple, disturbance, or quantum of that field. This does not mean the universe is made of waves in the simple sense of waves on water. A quantum field is not a mist spread through space, or a glowing ocean waiting just behind the wallpaper. It is a physical mathematical entity whose states obey quantum rules and whose excitations can appear as particles when they interact with other systems. That may sound less cozy than tiny beads, but it is far more successful. Nature, with its usual lack of concern for human comfort, seems to prefer the deeper version. Quantum field theory is the framework used to describe the known elementary particles and the interactions between them, except for gravity. It forms the foundation of the standard model of particle physics, which describes the electromagnetic interaction, the weak interaction, and the strong interaction. These are three of the four fundamental interactions known in nature. The fourth is gravity, and gravity is currently described best by Albert Einstein's general relativity rather than by the standard model. That boundary matters. Quantum field theory is not a finished explanation of absolutely everything. It does not yet provide a complete, experimentally confirmed quantum theory of gravity. It does not explain dark matter. It does not explain dark energy. It does not answer every question about why the universe has the particular particles and constants it has. A good scientific theory is not weakened by admitting where it stops. In fact, that honesty is part of what makes the map useful. A map that claims to include every path, every rabbit hole, and every suspiciously muddy shortcut is usually selling something. But within its proper domain, quantum field theory is astonishingly powerful. It explains how light and matter interact. It underlies the physics of atoms and molecules. It helps describe radioactive decay, particle collisions, antimatter, the behavior of electrons in materials, and the deep structure of forces inside atomic nuclei. It is part of the reason modern technology can include lasers, semiconductors, particle detectors, medical imaging, and the careful measurements that test the smallest known features of matter. So when this journey asks how quantum fields built reality, it is not claiming that fields assembled stones and stars like tiny invisible builders wearing hard hats. The meaning is deeper and quieter. Quantum fields provide the underlying rules from which the particles of matter, the forces between them, the stability of atoms, the glow of light, and the chemistry of life can emerge. The world still feels solid. A stone still has weight. A hand still meets the surface of a table and stops there. Stars still burn in distant darkness, and planets still move through the long curves of gravity. But beneath that familiar world is a less familiar one, where reality is not made first from little things, but from fields whose excitations become the particles that build the little things. The older picture of particles and forces was not foolish. It carried physics a very long way. It described falling apples, orbiting moons, flowing electricity, and the motion of planets with magnificent success. But it was not the final layer. Beneath the apparent certainty of ordinary matter, modern physics finds something more subtle. Fields everywhere, particles as excitations, interactions as structured exchanges, and solidity as an achievement rather than a starting point. Reality in this view is not less real because it is stranger than it looks. It is simply built from quieter foundations than the senses first suggest. Before quantum fields entered the story, physics already had a remarkably powerful way of describing reality. It was a world of objects, motion, and forces, a world where matter could be imagined as something solid and separate, moving through space as time flowed steadily onward. This older picture is often called classical physics, and for large, slow, everyday things, it remains beautifully useful. A rolling ball, a swinging pendulum, a falling stone, a planet circling the sun, all can be understood with impressive accuracy using the classical ideas that grew from Isaac Newton's work. Newton's great vision treated space and time as the grand stage on which events happened. Space was the arena, time was the steady clock. Objects moved through this arena, and their motion changed when forces acted upon them. In 1687, Newton published his laws of motion and his law of universal gravitation, setting out one of the most successful scientific frameworks ever written. The same kind of reasoning that described an apple falling toward Earth could also describe the moon curving around Earth and Earth curving around the sun. It was an enormous act of unification, and probably one of the best examples in history of noticing that the sky and the garden were playing by the same rules. Newton's laws of motion explained how objects resist changes in their motion, how force changes motion, and how forces between objects come in equal and opposite pairs. His law of universal gravitation described gravity as an attraction between masses. The larger the masses, the stronger the pull. The greater the distance between them, the weaker the pull. With this, the solar system became not a collection of mysterious celestial habits, but a system that could be calculated. This was not merely a poetic triumph. It worked. It predicted planetary motion. It explained tides. It helped later scientists and engineers understand projectiles, machines, bridges, ships, clocks, and eventually rockets. Classical mechanics became a language of confidence, a way to describe nature as if the universe were an enormous, elegant machine. But hidden inside that success was a question that would not go away forever. In Newton's picture, gravity acted across empty space. Earth pulled on the moon without a visible rope, rod, chain, hook, or cosmic bit of string. Newton himself was cautious about claiming to know the deep mechanism behind gravity. The mathematics worked, but the idea of action at a distance remained philosophically strange. It was as if nature had handed physics an excellent recipe, while politely declining to explain who had prepared the kitchen. For a long time, that was acceptable, because the calculations were so successful. Matter could be treated as particles or bodies. Forces could be treated as influences between them. Space and time could be treated as the background. The world seemed understandable as a collection of things pushing, pulling, colliding, orbiting, and falling. Then electricity and magnetism began to change the mood. In the 19th century, Michael Faraday introduced a way of thinking that felt very different from Newton's. Faraday was fascinated by electricity, magnetism, and the invisible patterns surrounding charged objects and magnets. He imagined lines of force spreading through space, not as decorative sketches, but as something physically meaningful. Around a magnet, iron filings arrange themselves into curved patterns because they are responding to a magnetic field. Around electric charges, other charges feel pushes or pulls because of an electric field. Faraday's field line suggested that space itself was not just an empty arena. Something could be present there, carrying influence from place to place. This was a major conceptual shift. Instead of saying only that one object affects another across a distance, field thinking says that an object creates a condition in the space around it, and another object responds to that condition where it is. The field becomes the middle part of the story. It is not simply object here, mysterious influence there, result somewhere else. It is object, field, interaction. That may sound like physics adding an extra step, but it gave nature a more local and continuous way to act. James Clerk Maxwell then gave Faraday's field ideas a powerful mathematical form. In the 1860s, Maxwell showed that electricity and magnetism were deeply connected parts of one electromagnetic theory. A changing electric field can create a magnetic field, and a changing magnetic field can create an electric field. Together, these changing fields can sustain one another and travel as a wave. That wave is light. This was one of the great revelations of physics. Light, which had seemed like its own separate mystery, became part of electromagnetism. The glow of a lamp, the warmth of sunlight, the colours of a rainbow, and the invisible radio waves that later technologies would use all belonged to the same family. They were electromagnetic waves, disturbances in the electromagnetic field travelling through space at the speed of light. With Maxwell, the field became harder to dismiss as a mere calculation trick. The electromagnetic field carried energy. It had momentum. It could travel. It could push charged matter. It could exist in empty space as light moving between stars and planets. If Newton's universe had been filled mainly with objects and forces, Maxwell's universe made room for something spread out, continuous, and physically real. So before quantum theory arrived, physics already had two great languages sitting side by side. One was the language of particles, bodies, and forces, sharpened by Newton into a system of astonishing power. The other was the language of fields and waves, developed through Faraday's imagination and Maxwell's mathematics into a new picture of invisible physical structure. Both languages worked. Both revealed something true, but they did not yet fit together into a single final picture. Matter still looked particle-like. Light now looked like a wave in a field. Forces could be described through laws, yet fields seemed to offer a deeper way for influence to move through space. Reality had become more sophisticated than a simple machine of little objects. It had acquired invisible structure, and that structure was not optional. Quantum field theory would later grow from this tension. It did not appear suddenly from a blank page, like a rabbit from a very intimidating mathematical hat. It emerged because physics already had particles, forces, waves, and fields, and each of them explained part of the world. The next challenge was to understand how these pieces could belong to one deeper description. The old classical picture was not wrong in the places where it works. It still guides spacecraft, buildings, engines, and the quiet arc of a thrown stone, but it was incomplete. Beneath particles and forces, the idea of fields had begun to take root, gently preparing physics for a stranger possibility, that fields might not just fill reality, but help create the particles that reality appears to be made from. Light seemed, for a while, to have found its place in physics. After James Clerk Maxwell, it could be understood as an electromagnetic wave, a self-sustaining ripple of electric and magnetic fields travelling through space. This was a beautiful idea, and more importantly, it worked. It explained radio waves, visible light, infrared radiation, ultraviolet radiation, and many other forms of electromagnetic radiation as members of the same family. Nature seemed to have taken several mysteries, placed them neatly in one drawer, and labelled the drawer rather elegantly. But physics has a habit of hiding its deepest problems inside things that first appear simple. Light from a hot object was one of those problems. A warm piece of metal glows faintly red. Make it hotter, and it becomes orange, then yellow-white, then dazzling. A star does something similar on a grander scale. Its colour depends strongly on temperature, with cooler stars glowing redder and hotter stars shining bluer or whiter. This pattern is not random. Hot objects emit radiation across a spread of colours and energies, and the shape of that spread depends on temperature. Physicists called the ideal version of this a black body. A black body is not necessarily black in ordinary appearance. It is a perfect absorber and emitter of radiation, a useful theoretical object that helps reveal the basic rules of heat and light. The problem was that classical physics could not correctly predict how much radiation such an object should emit at every colour. At lower frequencies, classical ideas worked reasonably well. But at higher frequencies, especially in the ultraviolet region, the prediction went badly wrong. The old theory suggested that a hot object should emit more and more energy at shorter and shorter wavelengths, without a sensible limit. This became known as the ultraviolet catastrophe, which is an excellent name for a failed calculation, and a rather dramatic name for something happening quietly inside an oven. The universe, fortunately, was not actually behaving catastrophically. Hot objects did not pour out infinite ultraviolet energy. The problem was not with nature. It was with the assumptions inside the theory. In 1900, Max Planck found a solution. He was trying to describe blackbody radiation correctly, and he introduced a strange idea that would become one of the foundations of quantum physics. Planck proposed that energy could be exchanged only in discrete packets, rather than in any completely smooth amount. These packets were later called quanta. This was not originally presented as a full philosophical revolution. Planck was, in some ways, using a mathematical step to make the calculation work. But the step was extraordinary. It suggested that energy exchange at the microscopic level might not be continuous. Instead of flowing in infinitely divisible amounts, energy came in allowed portions, with the size of each portion depending on the frequency of the radiation. The higher the frequency of the light, the larger the energy packet. The lower the frequency, the smaller the packet. This idea brought the blackbody spectrum into agreement with observation. It solved the ultraviolet catastrophe by showing that very high-frequency radiation required larger energy packets, making those emissions much less likely at ordinary temperatures. A crack had opened in the smooth classical picture. Then, in 1905, Albert Einstein pushed the idea further. He considered the photoelectric effect, a phenomenon in which light shining on a metal surface can knock electrons out of the metal. Classical wave theory might suggest that brighter light should always be better at ejecting electrons, because brighter light carries more total energy. But experiments showed something more specific and more puzzling. Light below a certain frequency could fail to eject electrons no matter how bright it was. It could shine more intensely, but still not free the electrons. Light above that frequency, however, could eject electrons even at low intensity. The key was not simply how much light arrived overall. The key was the energy carried by each individual packet of light. Einstein explained this by treating light as if it arrived in particle-like packets. These packets later became known as photons. A photon is a quantum of the electromagnetic field. It is not a tiny glowing ball, and it should not be pictured as a miniature bead of light flying through darkness with heroic determination. But it behaves, in important interactions, as a discrete unit of electromagnetic energy. In the photoelectric effect, an electron in the metal absorbs energy from a single photon. If that photon has enough energy, the electron can escape the metal. If the photon does not have enough energy, making the beam brighter only sends more insufficient photons. It is like sending more coins to buy something, but each coin is from the wrong currency, and the vending machine has absolutely no sympathy. This clarified a crucial distinction. Light intensity and photon energy are not the same thing. Increasing intensity means increasing the number of photons arriving, or increasing the total energy delivered by the beam. Increasing photon energy means increasing the frequency of the light. A dim ultraviolet beam can eject electrons if its photons have enough energy. A bright red beam may fail if each photon carries too little energy. This did not destroy Maxwell's theory. Light still has wave-like behavior. It still interferes, diffracts, and travels as electromagnetic radiation. Maxwell's equations remained one of the great achievements of physics. But the smooth classical wave picture was no longer enough on its own. Light could not be described only as a continuous wave spread through space. In certain interactions, it behaved as though energy came in individual quanta. The full field-based meaning of the photon would take more time to develop. Only later, through quantum field theory, Would the photon be understood as an excitation of the electromagnetic field itself? That deeper view would allow light to be both field-like and particle-like without forcing nature into one familiar everyday category. For now, the important change was already clear. The electromagnetic field, once imagined as smoothly waving through space, had revealed a grainy quantum structure beneath its surface. The wave had not vanished. The particle had not simply replaced it. Instead, light had become something stranger and richer than either older picture alone could hold. Reality had begun to speak in quanta. Once light had begun to behave like something grainy, matter answered with a strangeness of its own. The old picture had placed matter on one side and waves on the other. Matter was supposed to be made of particles, little pieces of substance with positions, paths, and mass. Waves belonged to water, sound, light, and fields. It was a tidy division, and like many tidy divisions in physics, it eventually began to look suspicious. The atom was the place where this suspicion became impossible to ignore. By the early 20th century, experiments had shown that atoms contained a tiny, dense, positively charged nucleus, surrounded somehow by electrons. But classical physics struggled badly with this arrangement. An electron moving around a nucleus should, according to classical electromagnetic theory, radiate energy and spiral inward. Atoms should not remain stable. Matter should collapse into a rather disappointing cosmic pudding. Niels Bohr offered a bold early solution in 1913. He proposed that electrons in atoms could occupy only certain allowed energy levels. They could not simply orbit at any distance with any energy they liked. When an electron moved between these allowed levels, it absorbed or emitted light with a specific energy. This helped explain atomic spectra, the distinct colours of light emitted or absorbed by different elements. Each element had its own pattern, almost like a barcode written in light, though considerably less useful at supermarket checkouts. Bohr's model was not the final theory of the atom, but it was a crucial step. It showed that stability and light emission could be understood only if atomic energy was quantized. Electrons were not behaving like tiny planets. They followed rules that had no comfortable classical equivalent. Then, Louis de Broglie made the picture stranger still. In 1924, he proposed that matter itself has wave-like properties. If light, once treated as a wave, could behave in particle-like ways, perhaps particles such as electrons could behave in wave-like ways. De Broglie connected a particle's wavelength to its momentum, meaning that moving matter could have an associated wavelength. For everyday objects, that wavelength is so incredibly tiny that it disappears from ordinary experience. A thrown stone has a matter wavelength, but no one needs to worry about it diffracting through a garden fence. The fence may relax. For electrons, however, the wavelength can matter. Their wave-like behaviour is not just a philosophical ornament, it can be measured. In 1927, Clinton Davison and Lester Germer provided important evidence when they observed electron diffraction from a crystal of nickel. The electrons scattered in patterns that made sense if they had wave-like properties. A beam of electrons, supposedly made of particles, could produce interference behaviour associated with waves. Matter itself had crossed the old boundary. This did not mean electrons were simply little waves of stuff spread out like ripples on a pond. The deeper theory was more subtle. Erwin Schrödinger developed wave mechanics, introducing the wave function as a mathematical description of a quantum system. The wave function contains information about the possible outcomes of measurements, but it's not an ordinary physical wave like a sound wave or a water wave. It does not describe a material substance sloshing through space. It describes the quantum state. Max Born then gave the wave function one of its most important meanings. He proposed that the wave function should be understood in terms of probability. More precisely, it could be used to calculate the probability of finding a particle with certain properties when a measurement is made. This was a major departure from classical physics. The theory did not simply give a definite path waiting to be revealed. It gave probabilities for possible results. That change was not a small adjustment. Classical physics had imagined that if enough information were known, the motion of a particle could be predicted with exact certainty. Quantum theory suggested something different. At the deepest level available to measurement, nature did not always provide a single hidden classical path. It provided a structured pattern of possibilities, and experiments revealed individual outcomes from that pattern. Werner Heisenberg sharpened this break with the uncertainty principle. The uncertainty principle says that certain pairs of properties, such as position and momentum, cannot both be known with unlimited precision at the same time. This is not because instruments are clumsy, although instruments, like everyone else, do have their off days. It is a limit built into quantum states themselves. A quantum object does not possess all classical properties in the exact way a tiny billiard ball was once imagined to possess them. Together, these ideas transformed the meaning of matter. Bohr showed that atomic energy levels were quantized. De Broglie suggested that particles had wavelengths. Davison and Germer showed electrons diffracting like waves. Schrödinger gave quantum behavior a wave function. Born connected that wave function to probability. Heisenberg showed that exact classical paths could not survive unchanged. Matter had stopped behaving like a simple collection of tiny solid things. Light had already gained particle-like features. Now matter had gained wave-like features. Physics could no longer honestly say that the universe was made from particles on one side and waves on the other. Both descriptions worked, but neither was complete alone. A deeper language was needed, one that could hold particles, waves, probability, measurement, and fields without forcing reality into familiar shapes it had quietly outgrown. By this point, light had stopped being only a wave, and matter had stopped being only a collection of little objects. The old categories were still useful, but they had softened at the edges. Photons carried light in discrete quanta. Electrons could diffract like waves. Atoms were stable only because their energy levels obeyed quantum rules. The universe was beginning to look less like a machine of tiny parts and more like a set of hidden instructions, quietly refusing to behave like common sense had politely requested. Yet another great idea was waiting nearby. Quantum mechanics had changed the meaning of particles, waves, and measurement, but it still had to face Albert Einstein's special relativity. Special relativity began with two simple but deeply unsettling principles. The first is that the laws of physics are the same for observers moving at constant speed relative to one another. A person doing a careful physics experiment inside a smoothly moving train should find the same basic laws as a person doing the same experiment on the platform, assuming neither is accelerating. The second principle is that the speed of light in a vacuum is the same for all such observers, no matter how the source of light or the observer is moving. That second statement is where everyday intuition quietly packs a bag and leaves. In ordinary life, speeds add and subtract. A ball thrown forward from a moving train appears faster to someone standing outside. But light does not obey that simple rule. Its speed in a vacuum remains constant. To make this possible, space and time themselves must adjust. Moving clocks run differently. Lengths along the direction of motion change. Events that seem simultaneous to one observer may not be simultaneous to another. Special relativity did not merely alter mechanics. It changed the stage on which mechanics happened. Ordinary quantum mechanics worked brilliantly for many problems. It explained atomic energy levels, chemical bonding, spectra, electron behavior, and the structure of matter with astonishing success. For the world of atoms and molecules, where particles often move much slower than light, and the number of particles can usually be treated as fixed, Schrödinger's wave mechanics and related quantum tools were wonderfully powerful. But nature is not always so polite. In high-energy physics, particles can move close to the speed of light. Collisions can concentrate enough energy into a tiny region for new particles to appear. Particles can also disappear, transforming into other particles, radiation, or energy shared among several products, as long as conservation laws are obeyed. Energy, momentum, electric charge, and other conserved quantities still have to balance. Nature may be strange, but it is not sloppy with its accounts. This was a problem for ordinary quantum mechanics. The original form of the theory was not naturally built for situations where particle number changes. It could describe an electron in an atom, but high-energy particle physics required something more flexible. A theory was needed that could respect quantum rules, obey special relativity, and allow particles to be created and destroyed during interactions. Paul Dirac made one of the most important steps toward that deeper theory. In 1928, he developed the Dirac equation, a relativistic quantum equation for the electron. It successfully incorporated special relativity into the quantum description of an electron and naturally included a property called spin. Spin is not ordinary spinning, like a tiny planet rotating on its axis. It is an intrinsic quantum property that affects how particles behave in magnetic fields and how they fit into the wider structure of matter. The Dirac equation did something even stranger. It seemed to imply the existence of a particle like the electron but with opposite electric charge. At first, this was not an easy result to interpret. Mathematics had pointed towards something unexpected, and physics had to decide whether it was a real feature of nature or an awkward sign that the theory had wandered into a cupboard and knocked over the furniture. Then, in 1932, Carl Anderson found experimental evidence for the positron while studying cosmic rays. Cosmic rays are high-energy particles from space that strike Earth's atmosphere and can produce showers of secondary particles. Anderson observed tracks in a cloud chamber that matched a particle with the electron's mass but with positive electric charge. Antimatter was real. It was not merely a mathematical inconvenience waiting to be swept under the rug. This discovery changed the mood of quantum theory. If particles had corresponding antiparticles, and if energy could produce particle-antiparticle pairs under the right conditions, then the theory of nature had to allow more than fixed little objects moving along quantum paths. It had to describe a world in which the number of particles could change, where fields could give rise to particle-like excitations and absorb them again. That is why quantum field theory became necessary. It could combine quantum mechanics with special relativity. It could treat particles not as permanent tiny beads, but as excitations of underlying fields. It could describe creation, annihilation, scattering, decay, and transformation within one framework. Wave functions had opened the door to a deeper view of matter. Relativity widened the doorway. Antimatter stepped through it, looking rather pleased with itself. The next step was to stop asking only where particles go and start asking what deeper fields make particles possible at all. The discovery of antimatter made one thing increasingly difficult to ignore. A theory of the smallest parts of nature could not treat particles as permanent little objects simply moving through space, as though the universe were a tiny billiard table with excellent mathematical manners. In high-energy physics, particles could appear. Particles could disappear. One set of particles could transform into another. Light could be emitted or absorbed. Matter and antimatter could be produced from energy, and then vanish again into other forms, provided the deep conservation laws of nature were respected. Energy had to balance. Momentum had to balance. Electric charge had to balance. Other quantum properties had to be accounted for as well, but the number of particles did not have to stay fixed. This was a profound change. Ordinary quantum mechanics had already replaced definite classical paths with wave functions, probabilities, and uncertainty. But many versions of early quantum mechanics still began by asking how a certain particle behaved. The particle was already there. The wave function described its quantum state. That approach worked beautifully for many atomic problems, where the number of particles could be treated as stable enough for the calculation. Particle physics needed something deeper. It needed a language where particles were not the permanent starting point, It needed a theory in which the field itself was the basic object, and particles were what appeared when that field carried a particular quantum of excitation. That language became quantum field theory. The central idea is simple to say, even if the mathematics beneath it is famously less inclined to offer tea and biscuits. Quantum field theory treats fields as quantum objects. A field is something that can be present throughout space and time, but in quantum field theory, the field does not vary in any completely smooth and unlimited way. Its energy and excitations obey quantum rules. Under the right conditions, a field can have discrete excitations, and those excitations are what are detected as particles. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Later developments would describe quarks as excitations of quark fields, gluons as excitations of gluon fields, and other particles in the same general way. This changed the order of explanation. Instead of fields being added around particles emerge from fields. The early development of this idea involves several major figures. Paul Dirac, already central because of his relativistic equation for the electron, helped develop the quantum treatment of the electromagnetic field and the idea that radiation could be described through creation and destruction of light quanta. Wolfgang Pauli contributed deeply to the quantum theory of fields and to the principles governing particles with spin. Werner Heisenberg, Pascal Jordan and others helped shape the mathematical foundations of early quantum field theory. Enrico Fermi developed a theory of beta decay, showing how quantum field ideas could describe processes where particles transform, especially in the weak interaction. One important step was called second quantization. The name is not especially friendly. Sounds like a sequel made only for people who enjoyed the first quantization and wanted fewer snacks. But the basic shift can be stated gently. In ordinary quantum mechanics, a particle's wave function is often treated as the main object being studied. In second quantization, the fields themselves become the main objects. The field can gain or lose quanta. It can be excited in a way that produces what is observed as a particle. It can also lose an excitation when a particle is absorbed or transformed. This is why second quantization was so useful. It did not force nature to keep the same cast of characters from beginning to end. It allowed a collision to begin with two particles and end with several different ones. It allowed a charged particle to emit a photon. It allowed an electron and a positron to annihilate into radiation. It allowed energy concentrated in a small region to become new particle excitations, as long as the rules of conservation were satisfied. The mathematical tools used to describe these changes are known as creation and annihilation operators. In a full calculation, they are precise mathematical objects. In a voiceover-friendly picture, they can be understood as tools that raise or lower the number of quanta in a field. A creation operator represents adding an excitation to a field, while an annihilation operator represents removing one. They do not describe a tiny hand reaching into space to place a particle there, or a tiny cosmic vacuum cleaner tidying one away. They describe how the quantum state of a field changes. This made quantum field theory especially suited to particle physics. In particle accelerators, high-energy collisions do not behave like ordinary objects bouncing off one another. They are interactions between fields. The particles entering the collision are excitations of fields. The particles leaving the collision are also excitations of fields, sometimes of different kinds. The process is governed by conservation laws, interaction strengths, symmetries, and quantum probabilities. A collision between particles is therefore not merely a crash between tiny marbles. It is more like a rearrangement of field excitations. Energy and momentum flow through the interaction. Charges are conserved. Allowed transformations occur. Forbidden ones do not. The outcome is not usually predicted as a single guaranteed result, but as a set of probabilities for possible results. This was the birth of a much deeper picture of reality. Matter was no longer best described as little permanent pieces moving through a background. Light was no longer only a smooth electromagnetic wave. Particles and waves were becoming surface appearances of something more fundamental. Quantum fields whose excitations could behave particle-like when measured. The shift was subtle but enormous. Physics had moved from particles moving through fields toward particles emerging from fields, and once that idea was taken seriously, the familiar world of matter, light, radiation and interaction began to look like the visible surface of a quieter, stranger field-based reality beneath. A field sounds at first like something simple. The word belongs to open grass, quiet hills, and perhaps a few sheep making decisions of mysterious importance. In physics, though, a field means something more precise. A field is something that has a value at every point in space and time. It is not necessarily visible. It is not necessarily made of a substance in the ordinary sense. It is a way nature can assign physical information to the world around us. Temperature in a room can be imagined as a field. Near a radiator, the air may be warmer. Near a window, it may be cooler. Every point in the room has some temperature, even if no one is standing there with a thermometer looking serious. Wind over a landscape can also be described as a field. At each place, the air has a speed and direction. It may drift softly through a valley, rush over a hill, or swirl around a building with the confidence of something that has never once respected human hair. The electromagnetic field is deeper still. Around an electric charge, the electric field describes how another charge would be pushed or pulled. Around a magnet or moving charge, the magnetic field describes a different kind of influence. James Clerk Maxwell showed that electric and magnetic fields are connected, and that changing electric and magnetic fields can travel together as electromagnetic waves. Light itself belongs to this family. So a field is not just a mathematical decoration added after the real objects have finished doing the important work. A field can carry energy. It can influence matter. It can move disturbances from place to place. It can be part of the physical furniture of reality, even when it cannot be touched like wood or stone. A quantum field takes this idea and places it under the rules of quantum physics. That is where the picture becomes stranger and more powerful. A quantum field is not a visible mist spread through space. It is not a fog, fluid, fabric, or hidden jelly of the universe, tempting though some of those images may be on a tired evening. It is a physical mathematical entity whose possible states obey quantum rules. It can have a lowest energy state. It can be excited. Those excitations can appear as particles when they interact with detectors, atoms, or other fields. This is the central idea behind quantum field theory. The field is treated as the deeper object, and particles are treated as quanta of that field. A quantum is a discrete unit of excitation. In this view, a particle is not quite a tiny bead sitting inside a field, waiting to be discovered with a sufficiently determined magnifying glass. It is more like a localized event or disturbance in the field, one that can carry energy, momentum, mass, charge, spin, and other measurable properties. Each kind of fundamental particle is associated with a corresponding field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field, sometimes loosely described as the photon field because photons are the particle-like quanta associated with electromagnetic radiation. Quarks are excitations of quark fields. Neutrinos are excitations of neutrino fields. The Higgs boson is an excitation of the Higgs field. This is a very different picture from imagining the universe as an empty container sprinkled with tiny particles. The fields are present throughout space. A particle appears when a field is excited in a particular way, and when that excitation can be detected as a particle-like object. The particle is not an independent little thing glued on top of reality. It is what a quantum field does under certain conditions. The word particle remains useful because these excitations often behave like particles in experiments. They can arrive at detectors in individual hits. They can carry definite amounts of energy. They can scatter from one another. They can be counted. A detector in a particle experiment does not usually record a soft, poetic smear of possibility. It records clicks, tracks, flashes, and deposits of energy. Nature may be subtle, but laboratory equipment tends to be quite practical about it. At the same time, the field picture explains why particles of the same type are truly identical. Every electron is an excitation of the same electron field. There is no tiny factory stamping out electrons with slightly different personalities. One electron is not more handcrafted than another. Wherever an electron is detected, it reflects the behaviour of the same underlying field that can be excited anywhere in the universe. This helps make sense of a strange fact about fundamental particles. Two electrons are not merely very similar. As far as modern physics can tell, they are exactly identical in their basic properties. They have the same electric charge, the same mass, the same spin, and the same kind of behaviour. Quantum field theory explains this naturally because they are not separate little manufactured objects. They are excitations of one universal electron field. The same principle applies across the standard model of particle physics. The known elementary particles are understood through fields and their excitations. Matter particles, such as electrons, quarks, and neutrinos, arise from their own fields. Force-carrying particles, such as photons, gluons, and the W and Z bosons, arise from fields associated with interactions. The Higgs field plays its own special role by helping explain why certain elementary particles have mass. A quantum field is therefore not easy to picture, because it is not meant to be pictured in the same way as a chair, a river, or a cloud. It is understood through its effects, its equations, its symmetries, its interactions, and its measurable predictions. That may feel abstract, but it is not vague. Quantum field theory is one of the most precise frameworks ever built in science. The familiar world seems to begin with particles. Look more deeply, and the particles begin to look like the visible moments of fields. The field is present. The excitation appears, the detector responds, the particle is recorded. Beneath the solid world of things, quantum field theory offers a quieter foundation. Not empty space filled with little beads, but fields everywhere, capable of producing the events that reality presents as matter and light. The word particle is useful, but it can be a little misleading. It invites the mind to imagine something small, hard, and neatly located, like a grain of sand reduced beyond all ordinary seeing. An electron becomes a tiny bead. A photon becomes a bright little pellet of light. A quark becomes a speck tucked inside a proton or neutron, probably very busy and difficult to interview. Quantum field theory asks for a different picture. The particles detected in experiments are real, but they are not best understood as miniature pebbles of substance. They are quantized excitations of fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. A quark is an excitation of a quark field. Other particles follow the same deeper pattern. The field is the underlying physical structure, and what appears as a particle is a particular packet of field activity. This does not mean a particle is fake, imaginary, or only a symbol on a chalkboard. When a detector records an electron, it records a real event. When light hits the retina or a camera sensor, photons are involved in real energy transfers. The point is that the deeper explanation does not begin with a little object flying around like a microscopic marble. It begins with a quantum field, and with the ways that field can be excited, interact, and exchange energy. The word ripple can help, as long as it is treated gently. A ripple on a pond is not a separate pebble sitting on top of the water. It is a pattern of motion in the water itself. In a similar spirit, a particle can be thought of as a localized excitation of a field. But the comparison should not be pushed too far. A quantum field is not ordinary water, and a particle is not simply a little crest moving across a cosmic pond. Quantum fields obey rules that are far stranger and more precise than anything found in a garden pond. even one with suspiciously philosophical ducks. One of the great strengths of this field picture is that it explains why fundamental particles of the same type are identical. Every electron has the same electric charge, the same mass, the same spin, and the same basic behavior. One electron is not slightly more electron-like than another. There are no deluxe electrons, budget electrons, or electrons with optional extra legroom. In quantum field theory, this sameness makes sense because every electron is an excitation of the same electron field. Wherever an electron is found in the universe, it belongs to the same underlying field. This is very different from imagining particles as separately manufactured tiny objects. If electrons were little beads, one might reasonably wonder why every bead comes out exactly alike. The field explanation is cleaner. The electron field has certain properties, and its excitations appear with the properties that electrons have. The same principle applies to other fundamental particles. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. Neutrinos are excitations of neutrino fields. Their identities come from the structure and rules of the fields behind them. Those rules include properties such as mass, electric charge, and spin. Mass affects how a particle responds to forces and how it behaves in motion. Electric charge determines how it interacts with the electromagnetic field. Spin is an intrinsic quantum property, not ordinary rotation, even though the name makes it sound like something that should involve a tiny object enthusiastically turning around. These properties are not decorative labels. They determine how field excitations behave, which interactions they can take part in, and how they fit into the wider pattern of nature. A crucial difference among particles is the difference between fermions and bosons. Fermions include particles such as electrons, quarks, and neutrinos. They make up matter in the usual sense. Bosons include particles such as photons and gluons, and they are often associated with carrying interactions between matter particles. This is not a perfect everyday division between stuff and force, but it is a very useful starting point. Wolfgang Pauli identified one of the most important rules governing fermions, the Pauli exclusion principle. It states that identical fermions cannot occupy exactly the same quantum state at the same time. This principle is one of the quiet architects of ordinary matter. Without it, electrons in atoms would not arrange themselves into layered structures in the same way. They would be able to collapse into the lowest available state, and chemistry would lose the structure that makes elements behave differently. The Pauli exclusion principle helps explain why atoms have electron shells, why the periodic table has its pattern, and why matter resists being compressed. It is part of the reason a hand does not simply pass through a table. Electromagnetic repulsion matters deeply, but quantum structure matters too. The electrons in the atoms of the hand and the atoms of the table cannot all be pushed into the same states as though they were a crowd politely agreeing to become one very dense blob. Bosons behave differently. Identical bosons are not restricted by the Pauli exclusion principle in the same way. Many bosons can occupy the same quantum state, which is important in phenomena such as lasers and Bose-Einstein condensates. Photons, as bosons, can build up together in coherent light. Gluons, also bosons, are involved in the strong interaction that binds quarks within protons and neutrons. So the stuff of reality is not miniature classical machinery. It is field activity governed by quantum rules. Particles are not pebbles hidden inside space. They are the detectable excitations of fields, carrying properties shaped by symmetry, interaction, and quantum structure. The solidity of matter, the identity of electrons, the existence of atoms, and the pattern of chemistry all depend on this deeper behavior. The familiar world still appears to be made of things, and for everyday life that appearance is good enough. But beneath it, quantum field theory offers a quieter explanation. Matter is not assembled from tiny hard pieces in the simplest sense. It is woven from fields that can ripple, excite, interact, and organize themselves into the stable patterns called reality. After particles have been described as excitations of fields, a quiet question appears. What is left when there are no particles at all? If every electron, photon, quark and neutrino is a particular disturbance in a field, then empty space might seem to be what remains when the disturbances are gone. No ripples, no particles, no little flashes of detection, just nothing. But in quantum field theory, the vacuum is not nothing in the simple, everyday sense. It is not an empty container where all the physical activity has politely left the room. The quantum vacuum is the lowest energy state of the fields. It is what remains when a field has no real particles present, but it is still a field, obeying quantum rules, with structure built into its possible states. This is an important distinction. In ordinary speech, empty space means a place where nothing is there. In quantum field theory, empty space means a place where fields are in their lowest energy condition. That lowest condition is not the same as absolute blankness. It does not contain ordinary particles that can be counted like grains of sand, but it is not a dead absence either. The fields still exist. Their ground states still have properties. Their behavior still affects measurements. One way this appears is through zero-point energy. Zero-point energy is the energy associated with the lowest possible state of a quantum system. A classical object can, in principle, be completely still, with no motion and no leftover energy of that kind. A quantum system is different. Because of the uncertainty principle and the structure of quantum states, a field cannot simply be frozen into perfect stillness, with every relevant property exactly pinned down. This does not mean the vacuum is an unlimited power source. Zero-point energy is not a secret cosmic battery waiting to run cities, hover cars, or a kettle that boils before anyone remembers they wanted tea. In serious physics, zero-point energy reflects the quantum structure of fields. It matters in calculations and in subtle physical effects, but it should not be turned into a magical supply of usable energy. Nature is strange, but it is not usually that generous with the electricity bill. A famous example is the Casimir effect, named after Hendrik Casimir. In the late 1940s, Casimir predicted that two very closely spaced conducting plates could experience a tiny attraction because of how the plates affect the allowed modes of the electromagnetic field between them and around them. The key idea is that boundaries can change which field patterns are possible. When plates are placed extremely close together, the vacuum field modes between the plates are restricted compared with the modes outside. The result is a small measurable force. It is not large enough to pull planets together or rearrange furniture in a haunted laboratory. It is tiny. But it matters because it shows that the vacuum is not simply featureless emptiness. The allowed states of a field can be changed by physical boundaries, and those changes can have observable consequences. Another important clue comes from the Lamb shift, named after Willis Lamb. In hydrogen, the energy levels of the electron are not exactly what the simplest version of Dirac's theory would predict. Lamb and his collaborators measured a small difference between energy levels that should otherwise have matched in a more basic calculation. This subtle shift became one of the key successes of quantum electrodynamics, the quantum field theory of light and charged matter. The Lamb shift is connected to the way the electron interacts with the electromagnetic field, including effects associated with vacuum fluctuations. It shows that even the energy levels of the simplest atom are influenced by the quantum structure of the fields around and within it. Hydrogen may be the lightest atom, but it is not a simple little solar system. It is a quantum system embedded in fields whose behavior must be treated carefully. This is also where the phrase virtual particles often appears. It is a useful phrase, but a dangerous one if taken too literally. Virtual particles are not ordinary particles briefly popping into existence like tiny ghosts with excellent punctuality. They are mathematical features that appear in certain methods of calculation, especially perturbation theory. They help physicists calculate how fields interact, but they should not be imagined as normal particles secretly borrowing energy, having a quick stroll, and then vanishing before anyone checks the accounts. Real particles can be detected as actual excitations with measurable energy and momentum. Virtual particles are part of the internal structure of calculations. They are connected to the ways quantum fields influence one another, but they are not little hidden objects flitting through space in the ordinary sense. The language can be helpful, but only if it is handled gently, like a sleeping cat or an equation with a grudge. The deeper lesson is that the vacuum has structure. It is the lowest energy state of fields, not the absence of fields. Its properties matter for particle physics, for atomic energy levels, for forces between objects at very small separations, and for the consistency of quantum field theory itself. The vacuum is the quiet background condition from which real excitations can arise and into which they can be absorbed. This does not make empty space crowded in the everyday sense. It does not mean a dark room is secretly full of tiny particles bumping into the furniture. It means that the deepest description of emptiness is more subtle than common sense suggests. Remove the matter, remove the light, remove every detectable particle. The fields remain, resting in their lowest possible states, still carrying the quiet rules from which particles, forces, and measurable reality can emerge. So even emptiness participates in the story. The vacuum is not a blank stage beneath physics. It is part of the performance itself, silent most of the time, but never truly absent. The electromagnetic field was the first field to become truly familiar in modern physics, and it remains one of the best places to see quantum field theory working with almost unnerving precision. It is the field behind light, radio waves, magnetism, electric charge, chemical bonding, glowing screens, warm lamps, and the small electrical disagreements that sometimes occur between a sock and a carpet. The quantum field theory of this interaction is called quantum electrodynamics. It describes how charged particles, especially electrons, interact with photons, the quanta of the electromagnetic field. In this theory, an electron is not simply a little bead carrying charge through space, and a photon is not simply a tiny pellet of light. Both are excitations of fields, and their interaction is described through the rules of quantum mechanics and special relativity together. This matters because the electromagnetic interaction is everywhere in ordinary life. When light is emitted by an atom, quantum electrodynamics describes the interaction between the electron field and the electromagnetic field. When light is absorbed, the same basic field relationship is involved. When charged particles repel or attract is absorbed, the same basic field relationship when atoms form bonds, when electrons move through materials, and when light scatters from matter. Quantum electrodynamics is part of the deeper explanation. The modern form of quantum electrodynamics took shape after the Second World War, although its roots reach back earlier through Paul Dirac and the first attempts to quantize the electromagnetic field. Richard Feynman, Julian Schwinger, Sinéad Tominaga, and Freeman Dyson were central in turning quantum electrodynamics into a clear and usable theory. Feynman developed an intuitive and highly visual method based on diagrams. Schwinger produced powerful operator-based calculations. Tominaga independently developed related ideas in Japan. Dyson showed how these different approaches were mathematically connected and helped organize the theory into a coherent framework. The result was one of the most successful theories in science. Quantum electrodynamics could describe electrons interacting with photons while accounting for quantum uncertainty, special relativity, particle creation, particle annihilation, and the strange influence of the vacuum. It did not make the universe less strange. It made the strangeness calculable, which is one of physics' more impressive party tricks. Feynman diagrams became one of the most famous tools associated with the theory. They look like simple little drawings, lines meeting, particles entering, particles leaving, photons exchanged. Their simplicity is part of their charm, but they must be understood carefully. A Feynman diagram is not a literal photograph of what happens in empty space. It is not showing tiny particles travelling along drawn paths like commuters following a railway map. It is a compact visual tool for organising terms in a calculation. Each diagram represents a possible contribution to an interaction. More complicated diagrams include more internal processes and usually represent smaller corrections. When physicists add the relevant contributions, they can calculate probabilities for measurable outcomes. This is important because quantum theory rarely says, with classical certainty, exactly what must happen in a single event. It gives the probabilities for different possible results. One of the most striking tests of quantum electrodynamics involves the electron's anomalous magnetic moment. An electron behaves as if it has a tiny magnetic property connected to its spin. The simplest theory gives an approximate value, but quantum electrodynamics predicts tiny corrections caused by the electron's interaction with the electromagnetic field, including contributions from more complicated field processes. These corrections are incredibly small, but they can be measured and calculated with extraordinary precision. The agreement between theory and experiment for the electron's magnetic moment is among the most precise comparisons ever made in physics. It reaches to many decimal places, a level of accuracy so fine that ordinary intuition almost has nowhere comfortable to sit. This is not the kind of theory that merely gestures vaguely in the right direction. It predicts delicate details of nature with astonishing success. Yet quantum electrodynamics is not only about subtle laboratory measurements, it is also woven into familiar reality. Atomic spectra, the specific colours of light emitted or absorbed by atoms, depend on the quantum behaviour of electrons and photons. Chemical bonding depends strongly on electromagnetic interactions between charged particles, organised by quantum rules. Lasers depend on controlled light emission from atoms or other quantum systems. Electronics depends on electrons moving through materials under electromagnetic forces and quantum constraints. Everyday solidity also connects back to electromagnetic interaction. A hand does not pass through a table, partly because electrons and atomic nuclei in the hand interact electromagnetically with electrons and nuclei in the table, while quantum principles determine how electrons can occupy states in matter. The surface feels solid, but the deeper explanation involves fields, charges, allowed states, and interactions rather than tiny hard pieces touching like pebbles in a jar. Quantum electrodynamics therefore gives a concrete example of how quantum fields build the world that seems so ordinary. Light leaving a lamp, electrons shifting in an atom, a screen glowing in the dark, a molecule forming, a laser beam staying sharply organised. All of these depend on the interaction between charged matter and the electromagnetic field. It is easy for quantum field theory to sound impossibly abstract, as though it belongs only inside equations, particle accelerators, and blackboards filled with symbols that appear to be having a private argument. But quantum electrodynamics shows the opposite. A field theory can explain both the faintest corrections inside the hydrogen atom and the glow of the room around you. It can describe precise measurements made in laboratories and the ordinary behaviour of light and matter that fills daily life. The theory of light and charged matter is not the whole of quantum field theory. Other fields and forces are still waiting in the deeper structure of the standard model. But quantum electrodynamics shows the central idea in its cleanest and most tested form. Particles are excitations, interactions are field processes, and the visible world is shaped by invisible rules of remarkable precision. Quantum electrodynamics gave physics one of its most precise descriptions of nature, but its early success came with a rather alarming problem. When physicists tried to calculate how electrons and photons interacted, the mathematics often produced infinities, not large numbers, not awkwardly huge numbers that might make a calculator stare into the distance. Actual infinities. This was not a small inconvenience. A physical theory is supposed to predict measurable quantities. It should tell how strongly particles scatter, how energy levels shift, or how magnetic properties behave. If the calculation says the answer is infinite, while the laboratory politely measures something finite, then something has clearly gone wrong. Nature does not hand an electron an infinite mass or an infinite electric charge. An electron has a measured mass, it has a measured charge, it behaves in definite ways. The mathematics had to be repaired, or at least understood more deeply. The infinities appeared because quantum fields allow particles to interact with their own fields and with the vacuum in complicated ways. An electron is not just sitting peacefully in space, carrying charge like a tiny, well-behaved parcel. In quantum electrodynamics, it interacts with the electromagnetic field, and those interactions include layers of possible processes. The more carefully the field was treated, the more corrections appeared. Some of those corrections tried to become infinite. Renormalization was the method that made the theory usable. The basic idea is subtle, but it can be stated gently. Some quantities in the raw mathematics, often called bare quantities, are not directly measured in the laboratory. A bare mass or bare charge is a parameter inside the theory before all the field interactions surrounding the particle are taken into account. What experiments actually measure is the observed mass and observed charge after all those interactions have contributed. Renormalization absorbs the troublesome infinite or unmeasurable parts into the definitions of the measured quantities. Instead of pretending to observe a bare electron floating without its field effects, physicists work with the electron as it is actually measured. The theory is then organized so that finite testable predictions come out for real experiments. It is a little like discovering that the original price tag was written in nonsense, then building the accounting system around what can actually be paid, checked, and verified. Hans Bethe played an important early role in showing how this could work. In 1947, shortly after precise measurements of the Lamb shift, Bethe calculated a finite explanation for the shift, using ideas that pointed toward renormalization. The Lamb shift was a small difference in hydrogen energy levels, and it showed that the electron's interaction with the electromagnetic field had measurable consequences. Bethe's calculation helped demonstrate that the strange corrections of quantum electrodynamics could be tamed and connected to experiment. Richard Feynman, Julian Schwinger, Sinétira Tominaga, and Freeman Dyson then helped develop the successful renormalized form of quantum electrodynamics. Their methods differed in style, but together they transformed a troubled theory into one of the most accurate scientific frameworks ever created. Feynman's diagrams gave physicists a clear visual and calculational tool. Schwinger's approach was mathematically powerful and precise. Tominaga developed related ideas independently in Japan. Dyson showed how these methods were connected and helped place the theory on firmer ground. The result was remarkable. The same theory that had seemed threatened by infinities could predict tiny corrections to atomic energy levels and to the electron's magnetic behavior with extraordinary accuracy. Renormalization did not merely hide the problem under a rug and hope no one lifted the furniture. It revealed that the quantities directly available to experiment are already dressed by field interactions. The electron that appears in the laboratory is not a bare mathematical seed. It is an electron embedded in the quantum structure of its fields. For some time, renormalization still felt suspicious to many physicists. It worked, but it seemed almost too clever, as though the infinities had been persuaded to leave by a legal technicality. A deeper understanding came later through Kenneth Wilson and the renormalization group. Wilson showed that renormalization was not just a trick for removing infinities, it was a profound way of understanding how physics changes with scale. The same system can look different depending on the energy, distance, or resolution being used to study it. At low energies, many tiny details may not matter. At higher energies, deeper structures may become visible. A material can be described one way at the scale of everyday objects, another way at the scale of atoms, and another way still at the scale of fields and particles. The renormalization group explains how the parameters of a theory shift as the scale changes. This idea helped reshape the meaning of quantum field theory. It showed that a theory can be extremely accurate within a certain range without being the final description of all reality. This is the idea behind effective field theory. An effective field theory is not a failure because it has limits. It is a carefully built description that works within its proper domain. It can make precise predictions at accessible energies while leaving room for deeper physics at scales not yet reached. This is how much of modern physics operates. The Standard Model is extraordinarily successful at describing known elementary particles and 3 fundamental interactions, but it is not expected to be the final theory of everything. Gravity, dark matter, dark energy, and other open questions remain beyond it. Yet within its range, it works with stunning precision. Renormalization therefore turned a crisis into a strength. The infinities that once threatened quantum field theory forced physicists to ask what is actually measured, how theories depend on scale, and why different descriptions can be valid at different levels of reality. Instead of collapsing under impossible answers, quantum field theory became more careful, more flexible, and more powerful. The strange lesson is that a theory does not need to describe every depth of nature at once to be profoundly true. It needs to know where it works, how its quantities connect to measurement, and how its picture changes when the world is viewed more closely. In that quieter sense, renormalization did not merely save quantum field theory. It taught physics how to listen to nature at different scales. A quiet pattern runs beneath quantum field theory. It is not only a theory of fields, particles, and interactions. It is also a theory of rules that remain steady when the world is viewed in different but equivalent ways. These rules are called symmetries, and in modern physics they are far more than pleasing shapes or neat arrangements. They are part of the grammar of reality. In ordinary life, symmetry often means something visual. A butterfly has a kind of symmetry. A snowflake has a delicate symmetry. A face may be called symmetrical when both sides resemble one another, closely enough to satisfy the deeply suspicious committee inside the human brain. But in physics, symmetry means something broader. A symmetry is a transformation that leaves the essential laws unchanged. Imagine doing the same experiment in one room, then doing it again in another room. If the basic laws of physics are the same in both places, that is a kind of symmetry. The universe does not seem to have one set of electron rules for the kitchen and another for the garden shed, although the garden shed may contain more spiders than strictly necessary. Imagine doing an experiment today and then repeating it tomorrow. If the same physical laws apply at both times, that is another symmetry. Nature appears to have a deep consistency, a refusal to rewrite its basic rules every few minutes, which is considerate of it. These symmetries are not just philosophical comforts, they are tied directly to conservation laws. Emmy Noether showed this with extraordinary clarity in the early 20th century. Noether's theorem states that continuous symmetries are connected to conserved quantities. If the laws of physics do not change as time shifts forward, that symmetry is linked to conservation of energy. If the laws do not change from one place to another, that symmetry is linked to conservation of momentum. If the laws do not change under rotation, that symmetry is linked to conservation of angular momentum. This was a profound discovery. Conservation laws were no longer simply useful rules noticed from experience. They had a deeper origin in the structure of physical law itself. Energy is conserved not because the universe happens to be tidy, but because the laws of physics possess time translation symmetry. Momentum is conserved because the laws have spatial translation symmetry. Conservation is not merely bookkeeping, it is a sign of symmetry written into the foundation. In quantum field theory, symmetry becomes even more central. The behavior of fields is shaped by the symmetries they obey. These symmetries help determine which particles exist, how those particles interact, and which processes are allowed. A particle interaction is not just anything nature happens to feel like doing on a quiet afternoon. It must respect conservation laws, quantum numbers, field structure, and the symmetries of the theory. One especially important idea is gauge symmetry. Gauge symmetry is deeper and more abstract than simple movement through space or rotation. It involves the freedom to change certain internal descriptions of fields without changing the physical reality they describe. That may sound like a technical detail, but it is one of the great organizing principles of modern particle physics. In electromagnetism, gauge symmetry helps explain why the electromagnetic interaction has the form it does. It is connected to the existence of the photon and to the conservation of electric charge. The photon is the quantum of the electromagnetic field, and charged particles interact through that field according to rules shaped by gauge symmetry. The mathematics is elegant, but the physical meaning is concrete. The symmetry helps determine how light and charged matter are allowed to behave. Gauge symmetry also lies behind the weak interaction and the strong interaction. These interactions are described by more complicated gauge theories, where the symmetries involve internal relationships between fields rather than simple visible changes in ordinary space. In the 1950s, Chen-Ning Yang and Robert Mills developed Yang-Mills theory, a type of non-abelian gauge theory. In a non-abelian theory, the order of certain transformations matters, which makes the structure richer than in ordinary electromagnetism. At first, Yang-Mills theory was a bold mathematical framework in search of its full physical role. Over time, it became central to the standard model of particle physics. The strong interaction, described by quantum chromodynamics, is a Yang-Mills type theory involving quarks and gluons. The electroweak theory, which unifies electromagnetism and the weak interaction at high energies, also depends on gauge symmetry. What began as an abstract idea became part of the working architecture of known particle physics. This is one reason quantum fields do not behave randomly. Their interactions are tightly constrained. Symmetry tells the theory what kind of terms are allowed, what charges must be conserved, and what particles can appear in interactions. If a proposed process violates the necessary conservation laws or symmetries, nature does not merely frown at it. It does not happen, at least not within that theory. Symmetry also helps explain why different particles belong to families and why forces have the carriers they do. Photons, gluons, and the particles associated with the weak interaction arise within field theories built around specific gauge symmetries. The existence and behavior of these force-carrying particles are not arbitrary decorations. They are tied to the structure of the fields themselves. The result is a picture of reality that is stranger, but not chaotic. Quantum fields may fluctuate. Particles may appear and disappear in interactions. Probabilities may replace simple classical certainty. Yet beneath all that movement is an exacting structure. Symmetry acts like a quiet grammar, shaping what can be said in the language of fields. A sentence can be gentle, dramatic, brief, or sprawling, but grammar determines whether it holds together. In the same way, quantum field theory can describe many different processes, from light scattering to nuclear interactions, but symmetry determines which descriptions are physically meaningful. The universe is not merely full of fields, it is full of fields obeying rules so strict that they reveal conservation, interaction, and structure at the deepest levels known. Beneath the apparent messiness of matter and radiation, symmetry gives quantum fields their form. It is the hidden order that lets reality remain consistent while still allowing all the restless activity from which the visible world is made. The electromagnetic field is familiar because its effects are everywhere. Light reaches the eye. Electricity flows through wires. Magnets cling to fridge doors with a loyalty that can seem almost emotional. But not every field announces itself so plainly. Some of the most important processes in nature happen quietly inside atomic nuclei and stars, far from ordinary senses. One of these hidden processes belongs to the weak interaction. The weak interaction, often called the weak force, is one of the fundamental interactions described by quantum field theory. It is responsible for certain kinds of particle transformation. Unlike electromagnetism, which acts between electrically charged particles and can reach across large distances, the weak interaction works over extremely tiny distances, far smaller than the width of an atom. Its name can be slightly misleading. It is weak compared with the strong interaction in electromagnetism at everyday nuclear scales, but it is not unimportant. Without it, the universe would be profoundly different. One of the most important examples is beta decay. In beta decay, one type of particle inside an atomic nucleus can transform into another. A neutron can change into a proton while emitting an electron and an antineutrino. In another form, a proton can change into a neutron while related particles are emitted or absorbed. These processes are not just rearrangements of little balls inside a nucleus. They involve deeper transformations between quarks mediated by the weak interaction. Enrico Fermi developed an early theory of beta decay in the 1930s. His theory was not the final modern version, but it was a crucial step. It treated beta decay as direct interaction between particles and helped organize the strange evidence surrounding electrons, nuclei, and neutrinos. The neutrino itself had been proposed by Wolfgang Pauli to explain missing energy in beta decay, and Fermi gave the particle its name. The neutrino was, for a long time, an almost ghostly idea, not because it was supernatural, but because it interacts so weakly with matter that enormous numbers can pass through the body every second without leaving a trace. A rather dramatic entrance with no social commitment. Fermi's theory worked well at low energies, but it was not the deeper field theory that physics eventually needed. As gauge symmetry became central to quantum field theory, physicists began to realize that the weak interaction and electromagnetism might not be entirely separate. They appear very different in ordinary conditions. Electromagnetism has infinite range, carried by the massless photon. The weak interaction has an extremely short range, carried by heavy particles. But at very high energies, the two interactions can be understood as parts of a unified electroweak theory. This unification was developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their electroweak theory showed that electromagnetism and the weak interaction are two low-energy expressions of a single deeper framework. It is one of the great achievements of the standard model of particle physics. The theory depends on gauge symmetry and on the Higgs mechanism, which helps explain why the weak force carriers have mass while the photon remains massless. The weak interaction is carried by the W boson and the Z boson. These are massive force-carrying particles, unlike the photon of electromagnetism. Because they are so heavy, the weak interaction has a very short range. In simple terms, a heavy force carrier cannot mediate a long-range force in the same way a massless photon can. That is why electromagnetism can shape light from distant stars, while the weak interaction mostly reveals itself in nuclear and particle processes at incredibly small scales. The W boson and Z boson were discovered at CERN in the 1980s, confirming a major prediction of electroweak theory. Their discovery was a triumph for particle physics and a strong validation of the standard model. It showed that the weak interaction was not merely a mysterious nuclear effect, but part of a precise quantum field theory, with real force-carrying particles that could be produced and measured in high-energy experiments. The weak interaction is also woven into the life of stars. In the Sun, nuclear fusion begins with processes that depend on the weak interaction. When protons ultimately begin the chain that leads toward helium formation, one proton must transform into a neutron, producing a positron and a neutrino. This weak process is slow, and that slowness is important. If it happened much faster, the Sun would burn through its fuel far more quickly. The gentle sunlight reaching Earth depends, in part, on the weak interaction being weak enough to pace the Sun's nuclear furnace. Neutrinos are another major part of this story. They are produced in nuclear reactions in the Sun, in radioactive decay, in supernova explosions, and in particle interactions across the universe. Because they interact through the weak force and gravity, but not through electromagnetism or the strong interaction, they can pass through vast amounts of matter almost untouched. Detectors such as Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada have helped reveal their properties and confirm that neutrinos change type, a phenomenon known as neutrino oscillation. The weak interaction shows that quantum fields do more than explain light, charge, and familiar matter. They also describe hidden transformations that allow particles to change identity. They govern radioactive decay, influence the sun's slow burning, and produce neutrinos that stream through planets as if the planets are barely there. Reality is not built only from particles staying what they are. It is also built from rules that allow particles to become something else. The weak interaction is one of those rules, quiet and short-ranged, but essential to the deep machinery of atoms, stars, and the changing universe. At the centre of every ordinary atom sits a nucleus, and inside that nucleus are protons and neutrons. For a long time, protons and neutrons were treated as basic building blocks of matter. They were small, heavy, and tucked away in the atomic centre, while electrons occupied the surrounding quantum structure. But as particle physics looked more closely, the nucleus stopped looking like a simple collection of indivisible pieces. The deeper picture revealed another layer. Protons and neutrons are not elementary particles. They are made of quarks, held together by gluons, through the strong interaction. The quantum field theory that describes this interaction is called quantum chromodynamics. It is one of the central parts of the standard model of particle physics, and it explains how quark fields and gluon fields build the particles found inside atomic nuclei. The strong interaction has a fitting name. At the scale of atomic nuclei, it is enormously powerful. It is strong enough to bind quarks together inside protons and neutrons, and it is also connected to the residual strong force that helps hold protons and neutrons together inside nuclei. Without it, atomic nuclei would not exist as they do. Without nuclei, there would be no ordinary atoms, no familiar chemistry, no planets made of rock and water, and no one lying quietly awake at night wondering whether quarks are having a nice time in there. The quark model was developed in the 1960s by Murray Gell-Mann and independently George Zweig. They proposed that particles such as protons and neutrons were made of smaller constituents. In the modern picture, a proton contains 2 up quarks and 1 down quark, while a neutron contains 1 up quark and 2 down quarks. This simple difference helps explain why protons and neutrons are similar but not identical. They belong to the same deeper family of particles called baryons, built from 3 quarks. But quarks are not held together by ordinary electric charge. They carry a different kind of charge known as colour charge. The name is a little unfortunate for anyone imagining tiny red, green and blue specks of paint. Colour charge has nothing to do with visible colour, paint, pigment, rainbows, or red paint having a lively social life. It is a label for the charge-like property that quarks carry under the strong interaction. Gluons are the force-carrying particles of the strong interaction. They are excitations of gluon fields, just as photons are excitations of the electromagnetic field. But gluons behave very differently from photons. Photons do not carry electric charge, while gluons themselves carry colour charge. This means gluons can interact with one another directly, making the strong interaction far more complex than electromagnetism. One of the strangest features of quantum chromodynamics is asymptotic freedom. David Gross, Frank Wilczek, and David Politzer helped discover this principle in the early 1970s. Asymptotic freedom means that quarks interact more weakly when they are extremely close together. At very short distances inside a proton or neutron, quarks can behave almost as if they are relatively free. That word almost is doing a great deal of work, like a tiny legal advisor sitting inside the sentence. But when quarks are pulled farther apart, the strong interaction becomes stronger. This is deeply unlike electromagnetism, where the force between charges becomes weaker with distance. With quarks, trying to separate them increases the energy stored in the gluon field between them. It is often compared to stretching a strong elastic band, although the real quantum field behavior is much more subtle. This leads to confinement. Under ordinary conditions, isolated quarks are not found freely in nature. If enough energy is added while trying to pull quarks apart, the energy does not simply free a single quark. Instead, it can produce new quark and antiquark combinations. The result is not a lonely quark escaping into the world with a small suitcase. It is new particles forming from the energy placed into the field. Confinement is one of the defining features of the strong interaction. Quarks are locked inside particles such as protons, neutrons, and mesons. This does not mean they are stuck by tiny ropes. It means the behavior of the gluon fields and the structure of quantum chromodynamics prevent isolated quarks from appearing under normal conditions. The field itself enforces the rule. Quantum chromodynamics also changes the way mass should be understood. It would be natural to imagine that the mass of a proton simply comes from adding up the masses of its quarks. But that is not the main story. The bare masses of the up and down quarks inside a proton account for only a small fraction of the proton's total mass. Much of the mass comes from the energy of the strong interaction itself, the energy of the gluon fields, the motion of the quarks, and the dynamic field activity inside the proton. This means that most of the visible mass of ordinary matter is not simply the mass of tiny ingredients sitting still. It is largely energy bound up in quantum fields. The mass in atoms comes mostly from protons and neutrons, and the mass of protons and neutrons comes mostly from strong field energy. In a very real sense, the weight of ordinary matter is tied to the restless inner life of quantum chromodynamics. This is a remarkable shift in perspective. The nucleus is not a quiet pile of little solid balls. It is a field-governed structure, held together by quarks, gluons, color charge, confinement, and strong interaction energy. The same field-based logic that describes light and electrons also reaches into the heart of matter, where the atomic nucleus is built and stabilized. Quantum fields therefore do not merely explain the glow around matter or the electrons that shape chemistry. They also build the dense centers of atoms. Beneath every stone, every hand, every ocean, and every star, quantum chromodynamics helps hold together the protons and neutrons from which visible matter is made. Reality is not only ripples of light and delicate electron states. It is also the deep binding of quarks by gluon fields, a hidden strength at the center of atoms, quietly making the solid world possible. By now, the picture of reality has become much less like a box of tiny parts and much more like a quiet system of fields. The electromagnetic field gives rise to photons. Quark fields and gluon fields build the deep structure of protons and neutrons. The weak interaction allows particles to transform. But one field has a particularly strange role because it is not only involved in interactions. It helps explain why many elementary particles have mass at all. This is the Higgs field. The Higgs field is a quantum field with a value that is not zero even in empty space. That is the first unusual thing about it. Most fields can be imagined, very loosely, as being calm or unexcited when no particles are present. But the Higgs field has a background value throughout the universe. It is not switched off in the vacuum. It is present everywhere, quietly shaping the behavior of particles that interact with it. This idea is easy to misunderstand, so it needs to be handled carefully. The Higgs field is not a visible substance filling space. It is not a cosmic fog, invisible treacle, or universal sticky syrup slowing everything down as particles try to push through it, presumably while muttering about the inconvenience. It is a quantum field whose interaction with certain elementary particles affects the mass terms that appear in the standard model of particle physics. The Higgs mechanism was developed in the 1960s by several researchers working on related ideas. Peter Higgs is the name most commonly attached to it, but François Englert and Robert Brute also made essential contributions, as did Gerald Guralnick, Carl Hagen and Tom Kibble. Together, their work helped solve a serious problem in particle physics: how particles associated with the weak interaction could have mass without destroying the gauge symmetry that made the theory work. In the Standard Model, some elementary particles interact with the Higgs field. Through that interaction, they acquire mass. This includes particles such as electrons, quarks, and the W boson and Z boson of the weak interaction. Other particles do not interact with the Higgs field in the same way. The photon, for example, remains massless. This is why light can travel through a vacuum at the universal speed limit, while particles with mass cannot reach that speed. Mass, in this context, is not simply heaviness in the everyday sense. It is a property that affects how a particle responds to forces and how much energy is associated with its motion. A particle with mass resists changes in motion in a way a massless particle does not. The Higgs field helps set this property for many elementary particles. It does not act like friction. It does not continuously drag particles back. It is part of the structure that determines what those particles are like. The Higgs field also has a particle associated with it, the Higgs boson. Just as a photon is a quantum excitation of the electromagnetic field, the Higgs boson is a quantum excitation of the Higgs field. Finding it was one of the great goals of modern particle physics. In 2012, the ATLAS and CMS collaborations at CERN's Large Hadron Collider announced the discovery of a new particle consistent with the Higgs boson. This was a major confirmation of the Higgs mechanism and a landmark for the Standard Model. The discovery mattered because the Higgs field itself cannot simply be seen. Physicists looked for the particle-like excitation of the field, produced in rare high-energy collisions and identified through the particles it decayed into. The Higgs boson is unstable and vanishes extremely quickly, so detectors did not find it sitting quietly in a little particle chair. They reconstructed its presence from patterns in the collision debris, using enormous data sets, careful statistics, and detectors larger than many buildings. It is also important to be clear about what the Higgs field does not explain. Not all mass in the universe comes directly from the Higgs field. The mass of ordinary matter is mostly found in protons and neutrons, and most of the mass of protons and neutrons comes from the energy of the strong interaction inside them, not simply from the bare masses of their quarks. Quantum chromodynamics, with its gluon fields and strong field energy, does much of the heavy lifting for the visible mass of everyday objects. Still, the Higgs field is essential. Without it, electrons would not have the same mass they have. Quarks would not have the same masses. The W boson and Z boson would not have their observed masses, and the weak interaction would behave very differently. Atomic structure, chemistry, and stable matter depend sensitively on the masses of particles. Change those masses too much, and the familiar patterns of atoms and molecules would not form in the same way. The electron's mass helps determine the size and behavior of atoms. Quark masses help shape the properties of protons, neutrons, and atomic nuclei, even though most of their mass comes from strong interaction energy. The masses of the weak force carriers help make the weak interaction short-ranged, affecting radioactive decay, neutrino processes, and the nuclear reactions that help stars shine. So the Higgs field is one of the clearest examples of a field filling space and shaping reality directly. It is not just a background detail in an equation. It helps determine the properties of the particles from which matter is built. The familiar world depends not only on particles existing, but on those particles having the right masses, the right interactions, and the right relationships to the fields beneath them. Reality is therefore not built only from excitations of fields. It is also shaped by the quiet values those fields hold, even in empty space. The Higgs field is one of those hidden foundations, present everywhere, almost silent, yet deeply involved in why matter has the form it does. The Standard Model is the closest thing modern physics has to a working inventory of the known elementary particles. It is not a list of everything that exists, and it is not a final theory of reality. But within its range, it is astonishingly successful. It gathers many of the fields, particles, and interactions of the microscopic world into one coherent framework, describing the electromagnetic interaction, the weak interaction, and the strong interaction through quantum field theory. In this picture, the universe is not built from a random pile of tiny objects. It is organized through fields. Each fundamental particle corresponds to a field, and what is detected as a particle is an excitation of that field. The standard model gives names, roles, and relationships to these excitations. It tells which particles make matter, which particles carry interactions, and how those interactions are constrained by symmetry, conservation laws, and quantum rules. The matter particles are known as fermions. They include quarks, charged leptons, and neutrinos. Quarks come in 6 types, called up, down, charm, strange, top, and bottom. The names are charmingly odd, as if particle physics briefly outsourced its vocabulary to a committee of poets and sandwich fillings. But the particles themselves are very real parts of the theory. Ordinary matter, the kind found in stones, oceans, air, stars, and sleepy human beings, mostly depends on up quarks, down quarks, and electrons. Up quarks and down quarks combine to make protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Electrons form the surrounding structure of atoms, shaping chemistry and allowing atoms to bond into molecules. Almost everything familiar in daily life is built primarily from these 3 matter particles, arranged by the strong interaction, the electromagnetic interaction, and the quantum rules that govern electron states. The charged leptons include the electron, the muon, and the tau. The electron is stable and central to ordinary atoms. The muon and tau are heavier relatives that appear in high-energy processes and decay quickly. Neutrinos also come in 3 known types: the electron neutrino, the muon neutrino, and the tau neutrino. They're extremely light, electrically neutral particles that interact mainly through the weak interaction and gravity. Vast numbers of neutrinos pass through Earth all the time, usually without noticing the planet in any socially meaningful way. The force-carrying particles are bosons. The photon carries the electromagnetic interaction. It is the quantum excitation of the electromagnetic field, responsible for light and for the interaction between electrically charged particles. Gluons carry the strong interaction. They bind quarks together inside protons, neutrons, and other strongly interacting particles. The W boson and Z boson carry the weak interaction, allowing certain particles to transform into others, as happens in beta decay and in important processes inside stars. The Higgs boson also belongs within the standard model, but it has a special role. The Higgs field is the field with a non-zero value throughout empty space. Certain elementary particles interact with this field, and through that interaction they acquire mass. The Higgs boson is not the field itself. It is the quantum excitation of the Higgs field, just as the photon is the quantum excitation of the electromagnetic field. The field is the deeper background structure. The boson is the detectable ripple. This distinction matters because the standard model is a field theory, not merely a particle catalogue. The particles are the visible entries, but the fields are the deeper language. Electrons, quarks, photons, gluons, neutrinos, weak bosons, and the Higgs boson are not independent little beads dropped into empty space. They are excitations of fields whose behaviour follows mathematical rules tested with extraordinary precision. Much of this testing has taken place through major laboratories and experiments. CERN in Europe has been central to discoveries involving the W boson, the Z boson, and the Higgs boson. The ATLAS and CMS collaborations at CERN's Large Hadron Collider announced the discovery of a particle consistent with the Higgs boson in 2012. Fermilab in the United States has played a major role in particle physics, including work on quarks, neutrinos, and precision measurements. Brookhaven National Laboratory has contributed to studies of high-energy nuclear and particle physics. SLAC National Accelerator Laboratory helped reveal the internal structure of protons through deep inelastic scattering experiments, strengthening the evidence for quarks. Earlier collider programs helped build the experimental path toward the Standard Model piece by piece. This long experimental history is important because the Standard Model was not invented as a decorative chart. It was built through theory and tested through collisions, decays, scattering patterns, detector tracks, energy deposits, and statistical evidence. Particle physics often studies things too small and too short-lived to be seen directly, so experiments reconstruct what happened from the traces left behind. It is less like photographing tiny marbles and more like understanding a storm by studying every raindrop, gust, and broken umbrella afterward. Yet the Standard Model is not complete. It does not include gravity. Gravity is described extremely well on large scales by Albert Einstein's general relativity, but a complete, experimentally confirmed quantum theory of gravity remains missing. The Standard Model also does not explain dark matter, even though astronomical evidence strongly suggests that dark matter exists. It does not explain dark energy, the name given to whatever is driving the accelerated expansion of the universe. It also does not fully explain neutrino masses, since the original Standard Model treated neutrinos as massless, while neutrino oscillation experiments show that they must have mass. So the Standard Model is both a triumph and a boundary. It organizes the known elementary particles and 3 of the 4 fundamental interactions with remarkable success. It explains the field-based machinery behind atoms, nuclei, radiation, particle transformations, and much of the visible structure of matter. But it also points beyond itself, toward deeper questions still unresolved. Reality's working inventory is therefore not the final warehouse. It is the most successful map so far of the fields and particles that build the ordinary world, precise enough to guide experiments across decades, yet incomplete enough to remind physics that the deepest shelves are not fully labelled. The Standard Model can sound like a map of a world far away, a place belonging to particle accelerators, detector halls, and equations that seem to have been designed by very patient minds with excellent coffee. But its fields do not stay locked inside laboratories. They are the same fields whose behaviour gives the ordinary world its texture, colour, chemistry, and light. The table, the air, the soft glow of a screen, the warmth of sunlight, the bonds inside a molecule, all of these are connected to the quantum rules of electrons, photons, and electromagnetic interactions. Atoms are the first bridge back to familiar reality. An atom is not a tiny solar system in the old picture, with electrons orbiting like small planets around a central sun. Electrons occupy quantum states around the nucleus. Their allowed energies are not continuous in the ordinary classical sense. They come in structured possibilities, shaped by the electron field, the electromagnetic field, the electric attraction between electrons and nuclei, and the rules of quantum mechanics. This is why atoms have distinct identities. Hydrogen behaves like hydrogen because it has 1 proton and 1 electron arranged according to quantum rules. Carbon behaves like carbon because its electrons fill available states in a pattern that allows particular kinds of bonding. Oxygen, nitrogen, iron, gold, and every other element owe their chemical personalities to nuclear charge, electron arrangement, quantum energy levels, and the Pauli exclusion principle. The periodic table is not a list of substances that happen to behave differently. It is a visible pattern produced by invisible quantum structure. Chemistry depends on this structure. When atoms form molecules, their electrons do not simply hook together like little mechanical clips. They occupy molecular orbitals, quantum states spread across more than 1 atomic nucleus. These orbitals help determine whether atoms bond, how strong the bond is, what shape the molecule takes, and how the molecule interacts with light and other matter. The electromagnetic interaction pulls negatively charged electrons toward positively charged nuclei, while electrons also repel other electrons. The final arrangement is a balance of attraction, repulsion, allowed quantum states, and energy minimization. Linus Pauling was one of the major figures in bringing quantum ideas into chemistry. His work helped explain the nature of the chemical bond using quantum mechanics, especially the way electron orbitals can combine and shape molecular structure. Quantum chemistry made it possible to understand why molecules have particular shapes and behaviors, rather than treating chemical bonding as a set of mysterious rules learned through memorization and mild suffering. The Pauli exclusion principle is especially important. It says that identical fermions, such as electrons, cannot occupy exactly the same quantum state at the same time. This rule helps build the layered arrangement of electrons in atoms. Without it, electrons would not spread into shells and orbitals in the same way. The variety of chemistry would collapse into something much less interesting, and the universe would be a poor place to run a bakery, a forest, or a nervous system. Solidity also begins to look different through this lens. A solid object feels firm not because atoms are tiny hard marbles pressed tightly together. Atoms are mostly empty space by volume. The firmness comes from electromagnetic repulsion, electron structure, and quantum state restrictions. When a hand presses against a table, the electrons in the atoms of the hand and the electrons in the atoms of the table interact through the electromagnetic field. Their quantum states cannot simply merge without consequence. The result is resistance, pressure, texture, and the very ordinary experience of not falling through the furniture, which is always a pleasant outcome. Light is woven into the same story. When electrons in atoms or molecules change energy states, they can absorb or emit photons. A photon is the quantum excitation of the electromagnetic field. The colours seen by the eye depend on which wavelengths of light are absorbed, reflected, scattered, or emitted by matter. The blue of the sky, the red of a glowing ember, the green of a leaf, and the sharp lines in an atomic spectrum all depend on the interaction between light and the quantum structure of matter. This is how quantum fields quietly enter daily life. The full machinery of quantum field theory is often most important in high-energy physics, where particle creation, annihilation, and relativistic effects must be handled carefully. But even when many practical technologies are described using ordinary quantum mechanics rather than full quantum field theory, the deeper field picture still underlies the particles and interactions involved. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. The interactions between them are the basis of much of the material world. Lasers rely on controlled emission of photons from quantum systems. Light-emitting diodes depend on electrons and holes in semiconductor materials recombining and releasing light. Semiconductors and transistors depend on the quantum behavior of electrons in solids, especially the structure of energy bands that determines whether a material conducts electricity easily, resists it, or can be carefully controlled. Modern electronics, from computers to phones, rests on the ability to guide electron behavior in materials with extraordinary precision. Magnetic resonance imaging depends on quantum properties of atomic nuclei, especially how nuclear spins respond to magnetic fields and radio waves. Particle detectors rely on the interactions of charged particles and photons with matter, turning invisible field excitations into tracks, flashes, signals, and data. Even the technologies used to test quantum field theory depend on quantum matter behaving reliably enough to build the machines. So the field-based picture is not remote from ordinary experience. It is the hidden logic beneath matter, chemistry, colour, and technology. The world feels solid because quantum fields and electromagnetic interactions organise atoms into stable structures. Molecules form because electron states and electromagnetic attraction permit them to. Light shines because photons are emitted, absorbed, and scattered through field interactions. Reality seems familiar because the deeper rules are so consistent. Beneath the warmth of a lamp, the shine of metal, the scent of a flower, and the tiny electronic decisions inside a screen, quantum fields are doing quiet work. They do not merely explain strange particles in distant laboratories, they help build the ordinary world, one electron state, one photon, one bond, and one interaction at a time. The ordinary world now looks wonderfully settled. Atoms exist, molecules form, light travels, form. Matter gathers into stars, planets, oceans, rocks, and living bodies that occasionally stare at the ceiling, wondering whether the universe had to be quite so complicated. But the universe did not begin in this calm, structured condition. Its earlier state was far hotter, denser, and more energetic than the one seen today. And in that extreme environment, quantum fields were not a hidden detail. They were central to the story. The Big Bang model describes the universe expanding from a much hotter, denser earlier state. It was not an explosion of matter into pre-existing empty space, like a firework bursting into a dark room. It was an expansion of space itself, carrying matter, radiation, and energy with it as the universe cooled. The earliest moments that can be studied with known physics were not filled with atoms, stars, or galaxies. Those structures formed much later. At first, the universe was a blazing field of high-energy particles, radiation, and interactions. At such extreme temperatures, particles could be created and destroyed constantly. Energy was dense enough that interactions between fields could produce particle-antiparticle pairs. Matter and antimatter could also annihilate back into radiation. In this hot early state, the distinction between particles as lasting objects and fields as the deeper structure becomes especially important. Particles were not fixed, little ingredients placed into the universe once and left alone. They were excitations arising from fields, transforming, colliding, vanishing, and appearing again as the young universe expanded and cooled. One of the most important transitions was electroweak symmetry breaking. At extremely high energies, electromagnetism and the weak interaction are understood as parts of a unified electroweak interaction. As the universe cooled, the Higgs field took on the non-zero value it has today throughout empty space. This changed the behavior of elementary particles. Particles that interact with the Higgs field acquired mass, and the weak interaction separated in behavior from electromagnetism. This transition helped shape the universe into the form known today. The photon remained massless, allowing electromagnetism to have long range. The W boson and Z boson became massive, making the weak interaction extremely short range. The masses of particles influenced how they moved, decayed, interacted, and participated in later cosmic processes. A change in a field value across the universe helped determine the properties of the particles that would eventually become atoms and matter. The early universe also raises one of the deepest unsolved questions in physics: why matter survived at all. In many high-energy processes, matter and antimatter are produced together. When a particle meets its antiparticle, they can annihilate into radiation. If the early universe had created exactly equal amounts of matter and antimatter, almost all of both should have vanished, leaving a universe filled mostly with light and very little material structure. Yet the observable universe is filled with matter. Stars, planets, dust, gas, and people are made from matter, not equal heaps of matter and antimatter. This imbalance is called baryon asymmetry. A baryon is a particle such as a proton or neutron made of 3 quarks. Baryon asymmetry refers to the fact that the universe contains far more matter than antimatter. The exact origin of this imbalance remains unresolved. Physicists know that certain conditions must have been involved, including processes that treat matter and antimatter slightly differently. But the full explanation is still an open question. It is one of those places where science has a clear mystery, not because the story is vague, but because the evidence points to something not yet fully understood. As the universe cooled further, particles stopped being created as easily from the background energy. Protons and neutrons formed. Later, simple atomic nuclei formed during Big Bang nucleosynthesis, producing mostly hydrogen and helium, with small amounts of other light nuclei. Much later still, electrons combined with nuclei to form neutral atoms, and light was able to travel freely through space. That ancient light is now observed as the cosmic microwave background. The cosmic microwave background is one of the strongest pieces of evidence for the hot early universe. It was studied in increasing detail by the COBE mission, the WMAP mission, and the Planck satellite. These missions measured the faint afterglow of the early universe and mapped tiny temperature variations across the sky. Those variations helped reveal the seeds of later cosmic structure. They do not directly show quantum fields like a photograph of tiny invisible machinery, but they test cosmological models that depend on early universe physics, including high-energy fields, radiation, expansion, and the growth of structure. Quantum fields also appear in discussions of cosmic inflation. Inflation is a leading framework suggesting that the very early universe underwent an extremely rapid expansion. Alan Guth helped introduce the idea in the early 1980s, and André Linde developed important versions of inflationary cosmology. Inflation can help explain why the universe appears so uniform on large scales, why it is so close to spatially flat, and how tiny early fluctuations could become the seeds of galaxies and galaxy clusters. Inflation is strongly motivated, but it is still an area with open theoretical questions. The exact field or mechanism responsible for inflation has not been confirmed. Many models exist, and observations continue to narrow what is possible. It should be treated as a powerful and important framework, not as a finished chapter with every line settled. The early universe shows quantum fields at their most cosmic. They did not only build atoms after the universe cooled. Their values, excitations, symmetries, and interactions help shape the transition from a hot, dense, rapidly changing state into a universe capable of structure. The fields beneath reality were present before stars, before planets, before chemistry, and before light could travel freely across space. The familiar world is therefore not just built from fields in the present. It carries the memory of fields in the beginning, when reality was hotter, simpler, denser, and far less settled, and when the rules of quantum fields helped decide what kind of universe could later unfold. Quantum field theory is one of the most successful frameworks ever created in science. It describes particles as excitations of fields. It explains how light and charged matter interact through quantum electrodynamics. It describes the weak interaction, the strong interaction, the Higgs field, and the structure of the Standard Model. Its predictions have been tested in particle accelerators, atomic measurements, magnetic measurements, nuclear processes, and technologies that now sit quietly inside ordinary life. But success is not the same as completion. A theory can be extraordinarily powerful and still not be the final layer of nature. Quantum field theory is like a map drawn with astonishing precision over a vast continent, while several mountain ranges at the edge remain covered in mist. The map is not wrong because the mist exists. It is simply honest to say where the lines become uncertain. The most famous missing piece is gravity. The Standard Model describes the electromagnetic interaction, the weak interaction, and the strong interaction. It does not include gravity. Gravity is described by Albert Einstein's general relativity, which treats gravity not as a force in the same sense as the others, but as the curvature of space-time caused by energy and mass. General relativity explains the motion of planets, the bending of light around massive objects, gravitational time dilation, black holes, and gravitational waves with remarkable success. The difficulty is that general relativity and quantum field theory speak very different mathematical languages. General relativity describes space-time as smooth and dynamic. Quantum field theory describes fields and particles through quantum probabilities, fluctuations, and interactions. When physicists try to describe situations where both must matter intensely, such as the center of a black hole or the earliest moments of the universe, the theories do not yet fit together in a fully tested way. A complete theory of quantum gravity remains one of the deepest open problems in physics. Several research programs attempt to approach it. String theory suggests that the most basic objects may not be point-like particles, but tiny vibrating strings with different vibrations corresponding to different particles. Loop quantum gravity attempts to describe space-time itself as having a quantum structure. Effective quantum gravity treats gravity as a quantum field theory that can work at accessible energies without claiming to be the final theory at all scales. Causal dynamical triangulations explores whether space-time geometry can emerge from more basic building blocks, arranged according to causal rules. These ideas are serious areas of research, but they are not settled answers. None has yet become a complete, experimentally confirmed theory of quantum gravity. The problem is not a lack of imagination. Physics has imagination in generous supply, occasionally too generous if left unsupervised near a blackboard. The challenge is connecting these ideas to evidence that can clearly distinguish one possibility from another. Quantum field theory also does not explain dark matter. Astronomical and cosmological evidence strongly suggests that galaxies, galaxy clusters, and the large-scale structure of the universe are influenced by matter that does not emit, absorb, or reflect light in the ordinary way. Dark matter appears through gravity, but its particle nature remains unknown. It may involve particles beyond the standard model, or something even less expected. So far, no dark matter particle has been confirmed. Dark energy is another unresolved piece. Observations of distant supernova, the cosmic microwave background, and large-scale cosmic structure indicate that the expansion of the universe is accelerating. Dark energy is the name given to whatever is driving the accelerated expansion. It may be related to the energy of empty space, or it may point to deeper physics not yet understood. The standard model does not explain it. In fact, the connection between quantum vacuum energy and the observed value of dark energy is one of the most puzzling mismatches in theoretical physics. Neutrino masses also show that the original standard model was incomplete. In the simplest original version, neutrinos were massless, but experiments have shown that neutrinos change type as they travel, a phenomenon called neutrino oscillation. This can happen only if neutrinos have mass. Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada played major roles in establishing this. Neutrinos are therefore small messengers from beyond the original standard model, quietly slipping through matter while carrying evidence that the theory needs extending. There is also the hierarchy problem. The Higgs boson has a measured mass, but quantum field calculations suggest that without some deeper explanation, the Higgs mass should be extremely sensitive to much higher energy scales. Physicists want to understand why it has the value it does without requiring what seems like delicate fine-tuning. Proposed solutions have included supersymmetry, composite Higgs models, and other forms of physics beyond the standard model, but no confirmed answer has yet emerged. Another open question is the matter-antimatter asymmetry of the universe. The known laws allow matter and antimatter to be created together, and when they meet, they can annihilate into radiation. If the early universe had produced exactly equal amounts of matter and antimatter, very little matter should have survived. Yet the visible universe is overwhelmingly made of matter. The standard model includes some differences between matter and antimatter behavior, but not enough to explain the observed imbalance. These gaps do not make quantum field theory weak. They define the frontier around one of the strongest theories ever built. Quantum field theory explains an enormous amount: atoms, light, particle interactions, nuclear processes, the Higgs field, antimatter, and much of the structure behind ordinary matter. But it also points beyond itself, toward gravity, dark matter, dark energy, neutrino masses, the hierarchy problem and the origin of matter's dominance over antimatter. The honest picture is not that physics has failed. It is that physics has succeeded so deeply that its remaining questions have become sharper. Quantum field theory built a vast part of the known description of reality, and at its edges it leaves quiet openings where the next layer of understanding may one day appear. Quantum fields built reality not in the sense of tiny workers assembling atoms with invisible tools, but in a deeper and more scientific sense. They provide the modern framework for understanding what particles are, how forces act, why matter is stable, how light behaves, how atomic nuclei hold together, and why the visible universe has the structure that it does. The familiar world of stones, stars, water, air, colour, warmth, chemistry, and living bodies is not separate from quantum fields. It is what their rules become when they are organised into stable patterns. The older picture began with objects. Isaac Newton described matter moving through space and time under the influence of forces, especially gravity. His laws of motion and universal gravitation revealed a universe that could be calculated with astonishing power. Planets, moons, tides, falling bodies, and thrown stones could all be understood through the same mathematical language. It was a magnificent achievement, and it remains deeply useful wherever speeds are low, objects are large, and quantum effects can stay politely in the background. But then fields entered the picture. Michael Faraday imagined invisible lines of force surrounding magnets and electric charges, giving space itself a kind of physical role. James Clerk Maxwell turned those ideas into electromagnetic theory, showing that electricity, magnetism, and light were connected. Light became a wave of the electromagnetic field travelling through space. Reality was no longer only a story of particles and forces acting across a distance. It now included fields spread through space, carrying energy, influence, and motion. Then the smooth wave began to crack. Max Planck, studying blackbody radiation in 1900, introduced the idea that energy could be exchanged in discrete packets called quanta. Albert Einstein, in 1905, explained the photoelectric effect by treating light as if it arrived in particle-like packets, later called photons. Light still behaved like a wave in many situations, but it also behaved like a collection of individual quanta when it interacted with matter. The electromagnetic field had revealed a grainy side beneath its smooth classical surface. Matter then answered with its own strangeness. Louis de Broglie proposed that particles such as electrons have wave-like properties. Erwin Schrödinger developed the wave function as a mathematical description of quantum behaviour. Max Born showed that the wave function should be understood in terms of probability. Werner Heisenberg's uncertainty principle revealed that certain pairs of properties, such as position and momentum, cannot both be known with unlimited precision. Matter could no longer be treated simply as little solid objects following exact paths. Paul Dirac then brought quantum mechanics into contact with special relativity. His relativistic equation for the electron described spin and led toward the prediction of antimatter. When Carl Anderson discovered the positron in cosmic rays, antimatter became real experimental physics, not just a strange mathematical echo. Nature had shown that particles could be created, destroyed, transformed, and paired with antiparticles. A deeper theory was needed, one that could handle quantum behaviour, relativity, and changing particle numbers at once. Quantum field theory supplied that deeper language. In this view, electrons, photons, quarks, gluons, neutrinos, W bosons, Z bosons, and the Higgs boson are not isolated little classical objects. They are excitations of fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons are excitations of gluon fields. Neutrinos arise from neutrino fields. The Higgs boson is an excitation of the Higgs field. The particle is the detectable event. The field is the deeper structure. This does not make particles unreal. A detector still records an electron. A photon still transfers energy. A proton still helps build an atomic nucleus. But the underlying explanation is subtler than tiny beads moving through emptiness. The fields are present throughout space, and their excitations appear as particles when they interact with other fields, atoms, detectors, or matter. Reality becomes less like a collection of miniature objects and more like a network of field activity governed by strict quantum rules. Those rules build the ordinary world. Solidity depends on electromagnetic repulsion, electron structure, quantum states, and the Pauli exclusion principle. A hand does not pass through a table because the charged particles in both interact through electromagnetic fields, and because electrons cannot all collapse into the same quantum state. Color depends on how photons are absorbed, emitted, reflected, and scattered by matter. Chemistry depends on electron energy levels, molecular orbitals, electric charge, and quantum rules. The structure of atoms is not a mechanical arrangement of little balls, but a stable pattern of field excitations and allowed states. Atomic nuclei depend on quantum chromodynamics, the field theory of the strong interaction. Protons and neutrons are built from quarks held together by gluons. Much of the mass of ordinary visible matter does not come simply from the bare masses of quarks, but from the energy of the strong interaction inside protons and neutrons. In that sense, the weight of the familiar world is partly the energy of fields bound into stable nuclear structure. Starlight also depends on fields. The sun shines because nuclear reactions transform particles and release energy, with the weak interaction helping regulate key processes in the chain of fusion. Radioactive decay depends on particle transformations described by quantum field theory. Lasers, light-emitting diodes, semiconductors, transistors, medical imaging, particle detectors, and much of modern electronics all depend on quantum behavior and electromagnetic interaction, with a deeper field picture sitting beneath the particles and forces involved. Quantum field theory does not make reality imaginary. It does not say the table is fake, or that matter is only a dream, or that the universe is less real because it is stranger than the senses first suggest. The table is real, the light is real, the atom is real, the star is real. But their reality emerges from structures that do not resemble everyday intuition. The familiar world is built from fields, excitations, symmetries, conservation laws, interactions, and probabilities. This is the quiet answer to how quantum fields built reality. They built it by giving matter its particles, light its quanta, atoms their structure, nuclei their binding, chemistry its patterns, and the visible universe much of its behavior. Beneath every solid surface and every beam of light, beneath color, warmth, mass, and material form, quantum fields provide the hidden architecture from which ordinary reality rises. Quantum fields built reality in the sense that they gave modern physics its deepest working description of particles, interactions, structures, and stable patterns. They are the framework beneath atoms and light, beneath matter and radiation, beneath the chemistry of living things and the technologies that glow quietly around the modern world. The familiar universe is not assembled from tiny hard pieces in the simplest possible way. It emerges from fields, excitations, symmetries, forces, and rules that operate far below ordinary sight. The path to this view began with the older classical picture of particles and forces, where Isaac Newton's laws made motion, gravity, planets, and falling objects understandable with extraordinary power. It widened through Michael Faraday and James Clerk Maxwell, who showed that fields were not merely convenient ideas but physically meaningful structures, with light itself revealed as an electromagnetic wave. Then Max Planck introduced quanta, Albert Einstein described light arriving in photon-like packets, Niels Bohr brought quantized energy levels into the atom, and Louis de Broglie suggested that matter itself had wave-like properties. The quantum picture deepened through Erwin Schrödinger's wave function, Max Born's probability interpretation, Werner Heisenberg's uncertainty principle, and Paul Dirac's relativistic electron. From there, quantum field theory became the language that could hold particles, waves, relativity, antimatter, creation, destruction, and transformation inside one larger framework. Quantum electrodynamics showed how electrons and photons interact with astonishing precision. Renormalization turned frightening infinities into workable predictions. Symmetry revealed the quiet grammar of fields, while electroweak theory, quantum chromodynamics, the Higgs field, and the Standard Model brought the known particles and three fundamental interactions into one coherent structure. This field-based picture is not a poetic metaphor. It is the working language of modern particle physics, tested in laboratories, colliders, atomic measurements, particle detectors, and technologies across the world. It explains why electrons behave as they do, why photons carry light, why quarks abound inside protons and neutrons, why atomic nuclei can exist, why chemical bonds form, why solids feel solid, and why light can be emitted, absorbed, and shaped into colours, lasers, signals, and screens. And yet, the picture is not complete. Quantum field theory does not yet include gravity in the same fully tested way. It does not explain dark matter. It does not explain dark energy. It does not fully account for neutrino masses in its original Standard Model form. The hierarchy problem and the matter-antimatter imbalance remain open questions. Its boundaries are real, and they matter. But within those boundaries, quantum field theory remains one of the most accurate and powerful scientific frameworks ever built. It does not make the world unreal. It makes the world deeper. A table is still solid. A star still shines. A molecule still holds together. A living cell still runs on chemistry. But beneath these familiar things are fields whose quiet rules give them shape. Reality is not less real because it is made from fields. It is real in a deeper, quieter, stranger way, like a simple song that seems familiar until each hidden instrument is heard, one by one carrying the whole melody beneath the surface.